Now this is where we can get away from having to do geometric equations all the time. We can use a Moore diagram. Now, not this week's lab, but next week's lab, we start doing Moore diagrams. And you'll see that, they're not that bad, and they are useful. A Moore diagram is drawn in a basic XY Cartesian type plot system, except instead of being X and Y, the two axes are shear stress and normal stress. Which means when we read a point off of it, it's telling us what the shear stress and normal stress are for that point on our rock or our hillside or whatever it is that we're plotting it for. That's good. Shear stress and normal stress are the things that we want to get. If we know sigma 1 and sigma 3, the primary stress, or the biggest primary stress, and the smallest, that's what we need to be able to draw one of these. Now we can write along the normal axis, because remember, sigma 1, 2, and 3 are always normal stresses. So we can plot them right along it. There's zero shear stress. And so this diagram doesn't have numbers, but supposing this was sigma 1 was 4 and sigma 3 was 1. So you'd go along the sigma n axis, put a dot at 4 and a dot at 1, and that's the start, where now you can draw a circle with a compass. You don't have to calculate it. You can find the center, throw the compass on there, line it up with a dot, spin, and you've got it your circle. Nice and easy. If you have a fracture because your object broke, like in that clay model, you can draw a line at 2 theta. You measure the angle theta, throw your protractor on here, measure 2 theta from the right. That's very important for this kind of Moore diagram, you're measuring from the right, and draw a line. Where that line hits your circle, called point P, you can just come down, read, hey, this is how much normal stress there is. Go over to the left, hey, this is how much shear stress there is. Basically the coordinates of that point. That tells you the shear stress and normal stress on your fracture plane. No equations. Just a piece of paper, draw your axes, graph paper is best, compass, protractor, boom, you're done. No calculator, anything. You do need the magnitude and orientations of the principal stresses. In the lab, this is easy. If air pressure, usually designated as 0 because 0 gauge pressure. For sigma 3, sigma 1 is whatever stress you're applying, so you know how much it is. The angle of the plane of failure, easy. It failed, you have it, measure it. Now, this might seem a little confusing here. This is where if you take that diagram for that clay block and you extend lines and you use all your triangle geometry, complementary angles, and so forth, turns out that the angle between the stress that's normal to the fracture plane and the sigma 1 is the same as the angle between that fracture plane and the plane sigma 3. Let me back up to the block. Okay, so the angle between sigma 1 coming down and this sigma n is the same as the angle between the failure plane and the sigma 3 direction. So that's theta, and angle right here between sigma 1 and sigma n is also theta. So if you don't have any graph paper and compass and protractor, but you do have a calculator, you can still get sigma n. This equation right here, sure, if you don't have a protractor, you're going to have to eyeball that fracture angle because you do need a theta. But other than that, no graph paper, no compass, and you can get your answer. Same for the shear stress. But the Moore diagram is easier, in my opinion, especially if you then go along same conditions. You have different materials fracturing at different angles. You can have that Moore circle, throw in a few different lines, and you see what the shear stress and normal stress is for every single one of them. Makes it easy to visualize, easy to show somebody, easy to make comparisons. If you have lots and lots of lines of equations, a lot of people don't like reading that. A lot of people will have a hard time visually comparing the results. You have a Moore circle, it makes it really easy.